Here is a situation that every computational scientist meets eventually. The mesh is built, the physics is right, the system is assembled. You press run, and the linear solver crawls. 200 iterations, and the residual has barely moved. Nothing is wrong with your model. What is wrong is the matrix, and the cure is a preconditioner. Over the next 20 minutes, we are going to build one from the ground up, incomplete LU factorization. We will start from ordinary Gaussian elimination, and we will finish at a multi-level method robust enough for two-phase flow, where a sharp interface can push a pivot to the edge of singularity. Every plot you will see comes from code that was actually run, not from a sketch. Here is the route, where the matrix comes from, why we cannot simply factor it, what a preconditioner really does to a spectrum, then the ILU family, in order of increasing sophistication, ILU0, ILUK, ILUT, the place where all of them break, and the multi-level idea that repairs it. We finish with benchmarks, including one that fails to prove what it was meant to prove. Almost every large linear system in fluid dynamics starts here. The incompressible Navier-Stokes equations, momentum balance on the left, and the incompressibility constraint underneath it, the velocity field must be divergence-free. Discrete has those equations, finite elements, finite volumes, it hardly matters, and you get a large sparse linear system with a very particular shape. 2 by 2 blocks. The momentum operator in the top left, the gradient and the divergence off the diagonal, and in the pure incompressible case, nothing at all in the bottom right. That zero block is not a detail. It is the reason this matrix is indefinite. It has eigenvalues on both sides of zero. Matrices like this are called saddle point systems, and they are famously unfriendly to iterative solvers. There is no positive definite structure to lean on. 4 things make this hard at once. The system is enormous. Millions of unknowns is routine. It is indefinite because of that zero block. It is non-symmetric because convection is not a symmetric operator, and its condition number grows as you refine the mesh, so the better your resolution, the worse your solver behaves. Now add a second fluid. Air and water in the same mesh means a density ratio near 1000 to 1 and a viscosity ratio near 50 to 1, and both of them jump discontinuously across the interface. That jump lands directly in the matrix coefficients. Keep this picture in mind. We will come back to it when things break. The obvious move is to solve the system exactly. Gaussian elimination, written in matrix form, factors A into a lower triangular L and an upper triangular U. Once you have them, each solve is 2 cheap triangular sweeps. So why not do that and go home? Because of this, on the left is the sparsity pattern of a genuine Poisson matrix, 5 non-zeros per row, and a great deal of empty space. Watch what elimination does to it. Every time we eliminate a column, entries that were structurally zero become non-zero. That is fill in, and it is relentless. On this small example, the factors carry 5 times the non-zeros of the original matrix. That sounds survivable. It is not, because the growth is superlinear. In 3 dimensions, the factors of an n by n matrix need memory of order n to the 4/3 and work of order n squared. Multiply that out for 10 million unknowns and you are asking for terabytes and days. So we give up on exactness. Instead, we use a Krylov method, GMRES f GMRES, biconjugate gradient stabilize, which only ever needs the matrix times a vector. Krylov methods are cheap per iteration. Their weakness is that on a badly conditioned matrix they need an enormous number of iterations. Which brings us to the actual subject of this lecture. A preconditioner is a matrix M that we use as a stand-in for A. Instead of solving AX equals B, we solve M inverse AX equals M inverse B. The solution is unchanged. What changes is the matrix the Krylov method actually sees. And that gives us the tension that governs this entire field. We want M close to A, because if M were exactly the preconditioned matrix would be the identity and we would converge in a single step. But we also need solving with M to be cheap because we do it at every iteration. Choose M equals A and each iteration costs a full direct solve. Choose M equals the identity and you have done nothing. Every method in this video is a different answer to that trade-off. Here is what success looks like, computed on a real convection diffusion matrix. On the left, the eigenvalues of A, smeared across 2 orders of magnitude, with values crowding towards 0. On the right, the eigenvalues of N inverse A using an incomplete factorization. They collapse into a tight cluster around 1. A Krylov method sees that cluster and converges fast. One caveat, because you will meet it in practice. Clustered eigenvalues guarantee fast convergence only for normal matrices. Convection-dominated flow gives you strongly non-normal matrices, where the spectrum can look beautiful while convergence is still slow. Treat the eigenvalue picture as strong intuition, not as a theorem. So here is the idea behind incomplete LU, and it is almost embarrassingly simple. We run Gaussian elimination, and we refuse to store the fill-in. The result is an approximate factorization. A is roughly L tilde times U tilde, with some residual matrix R that we never form and never look at. Because the factors are triangular, applying N inverse to a vector is still just a forward sweep and a backward sweep. The cost of one preconditioner application is proportional to the number of non-zeros we chose to keep. We control that number. That is the whole game. The strictest possible choice is ILU 0. Take the sparsity pattern of A and permit nothing else. The elimination loop is unchanged, but every update that lands in a position that was structurally 0 is simply discarded. L and U end up with exactly the pattern of the lower and upper parts of A. The advantages are real. Memory is known in advance and equals the storage of A. Setup is one sweep. There is nothing to tune. The disadvantage is equally real. For anything convection-dominated, or on a fine mesh, throwing away all fill-in throws away most of the information, and the preconditioner is simply too crude. Here is that statement as measured data. A convection diffusion problem with a coefficient jump of 1000. Unpreconditioned GMRES is still at 40% of its initial residual after 200 iterations, effectively stalled. The same problem with ILU 0 converges to machine precision in 43. From hopeless to routine, for the cost of one extra copy of the matrix. If dropping all fill-in is too aggressive, the natural next question is, can we keep the useful part? ILUK answers it structurally. Give every original entry level 0. When fill-in is generated at a position, give it a level equal to 1 plus the levels of the 2 entries that produced it, and keep it only if that number is at most k. So k equals 0 recovers ILU 0. K equals 1 admits 1 generation of fill, and so on. ILUK has an appealing property. The pattern can be computed before you touch a single number, and one serious flaw. It is purely combinatorial. A fill entry of size 10 to the minus 12 and a fill entry of size 10,000 are treated identically if they sit at the same level. On a matrix with strong coefficient jumps, that is exactly the wrong criterion. ILUT fixes that by dropping on magnitude instead of structure, with 2 parameters working together. Tau is a relative drop tolerance. After a row has been updated, any entry smaller than tau times the average magnitude of that row is discarded. That is the accuracy control. But a tolerance alone gives you no guarantee on memory. A nasty row could keep hundreds of entries. So the second parameter, P, is a hard cap. Of everything that survives the tolerance, keep only the P largest entries on each side of the diagonal. Tau buys accuracy, P bounds costs. The pattern is no longer chosen in advance, it emerges from the numbers. Here are 3 incomplete factorizations of one matrix. On the left, tau equal to 1/10, barely denser than A itself. In the middle, 100. On the right, 10 to the minus 4, at 3¼ times the non-zeros of a. You are watching the accuracy versus memory dial turn. And here is that dial plotted against what it buys. Iteration count in orange, fill in teal, as tau decreases from left to right. Loosening tau to 100th costs 4 to 5 iterations. Tightening it to 10 to the -4 costs about 50% more memory and takes you to 9. Beyond that, the curve flattens. You are paying for accuracy the Krylov method no longer needs. Notice what happens at the far left. At tau equal to 300ths and above, there is no data point at all. Because the factorization broke down, a pivot reached exact zero and the algorithm stopped. That is not a bug in the software. It is the fundamental vulnerability of incomplete factorization, and it is where the second half of this lecture begins. Every step of an elimination divides by the current diagonal entry, the pivot. A complete factorization protects itself by pivoting. If the diagonal entry is small, swap in a better row. Incomplete factorizations usually cannot afford that, because reordering rows destroys the sparsity pattern the whole method depends on. So when a small pivot appears, we divide by it anyway. The multipliers in that column become enormous. Those enormous numbers propagate into every subsequent row. The dropping rule, which compares entries against the size of their row, now sees a row dominated by garbage, so it drops the wrong things. One bad pivot does not cause one bad row, it corrupts everything downstream of it. And in two-phase flow, these pivots are not rare accidents. When you enrich the pressure space so that pressure can jump across the interface, Auss's-type enrichment is the standard example. The extra unknowns on cut elements are eliminated locally by static condensation. The size of the resulting pivot scales with how much of the element sits on each side of the interface. Now let the interface drift until it nearly touches a mesh node. The cut fraction goes to 0. The pivot goes to 0 with it. Nothing is wrong with the physics. The flow does not care where your nodes are, but your factorization has just been handed a row it cannot eliminate. A purely geometric accident has become an algebraic disaster. We can see this directly. For each row, take the absolute value of the diagonal entry and divide it by the sum of the absolute values of everything else in that row. Call it theta. A well-behaved row has theta around 1 or more. Here's that measure on a matrix where I planted 24 near singular rows, and there they are, 8 orders of magnitude below everything else, utterly isolated. Which suggests the key idea of this whole video. If a row cannot be eliminated safely right now, do not eliminate it. Set it aside. Eliminate everything that is well behaved, and then come back to the difficult rows afterwards when the matrix they live in has changed. Concretely, we test every row with theta against a threshold. Rows that pass go into a set F. Eliminate these now. Rows that fail go into a set C. Deferred. Permute the matrix so F comes first and it splits into 4 blocks. B, the well-behaved part, in the top left. The deferred coupling around it. Now factor only B incompletely with ILUT, and B is safe by construction because we chose it that way. Then eliminate B from the rest of the system. What is left over on the deferred unknowns is the Schur complement, C minus E times B inverse times R. This is exact block elimination. No approximation yet beyond the incomplete factorization of B itself. And here is the payoff, measured on the matrix from a moment ago. Before deferral, those 24 rows had a median theta of 3 times 10 to the minus 8. After the Schur update, the median theta of the same rows is 0.93. 7 orders of magnitude recovered, because the elimination of B pushed real information into the diagonal of those rows. A row that was unfactorable is now perfectly ordinary. The Schur complement is just another sparse matrix, so we do the whole thing again. Test its rows, split into good and deferred, factor the good part, form the next sure complement. Level after level, each level peels off the unknowns it can handle and passes the remainder downward. When what remains is small enough, we stop and factor it densely with full pivoting, where pivoting costs nothing because the block is tiny. Applying this thing is a recursion of its own. Split the right-hand side. Solve with B. Correct the deferred part. Recurse to the next level for the sure solve. Then come back up and correct the first block with the answer you just found. Down through the levels, then back up. 2 triangular solves and 2 sparse products at every level. On the matrix with the planted near singular rows, single-level ILU0 needs fortified iterations. The 2-level deferred version needs 22. Half the iterations from one structural change, refusing to factor the rows that were not ready. This is not a new invention, and you should know the names. ILUP is CK introduced inverse-based dropping and multilevel deferral. HILUCSI sharpen it for saddle point problems from partial differential equations, with both static and dynamic deferring and mixed symmetric and unsymmetric preprocessing across levels. If you are building in this space, those are the papers to read first. Which brings us to benchmarking and to the most useful part of this lecture, because the benchmark I am about to show you does not say what it was designed to say. The test problem, a 3-dimensional convection diffusion operator, 27,000 unknowns, a coefficient jump of 10 to the 5th standing in for a fluid interface, solve with GMRES restarted at 50. The results: plain ILU0. 47 iterations. Smooth aggregation algebraic multigrid, 95. Restricted additive Schwarz, 47. And the multilevel deferring method, 99 iterations, the slowest of the 4. On its own benchmark, the sophisticated method lost to the simplest one. So why? Because of how that test matrix was built. A consistent finite difference stencil produces rows whose diagonal exceeds the off-diagonal sum by about 1 part in 100 million. Every row is marginally dominant, so the deferring test sends essentially every row into F. Nothing is deferred, and the multilevel method degenerates into a single-level ILUT that is still paying for its multilevel bookkeeping. The lesson is worth more than the numbers. This benchmark demonstrates correctness and bounded overhead on an easy problem. It cannot demonstrate the method's value, because the test problem does not contain the pathology the method exists to cure. If your benchmark has no near singular pivots, do not use it to evaluate a method whose only job is to handle near singular pivots. One more result from the same study, because it is a useful warning about parameters. Holding everything else fixed and varying only the drop tolerance at 10 to the minus 3, 414 iterations. At 10 to the minus 4, 95. A single factor of 10 in one parameter and a factor of 4 in cost. Meanwhile, tripling the fill cap changed the answer by under 5%. Tune the tolerance first. So, practically, for Stokes flow or strongly diffusive problems, ILU0 on the velocity block is cheap and sufficient. For moderate Reynolds number, use ILUT and tune tau before anything else. When convection dominates, single-level methods start failing outright. Reach for multilevel ILU, or a block preconditioner that approximates the sure complement using the pressure mass matrix. And for two-phase flow with a sharp interface, fix the geometry first, shifting a distance field so the interface never sits on a node removes the bad pivots at their source, which beats every solver-side remedy. 4 things to take away. Incomplete LU is Gaussian elimination that refuses to store fill-in, and everything else is a choice about what to discard. ILU0 drops by structure. ILUT drops by value, which is what you want when coefficients jump. Every single level incomplete factorization is vulnerable to one small pivot, and in two-phase flow those pivots come from geometry, not from bad luck. And the multi-level answer is not a better dropping rule, it is deferring the rows that are not ready and letting a sure complement fix them. If you want to go deeper, the references on screen are the right starting points. Sod for incomplete factorization, Benzi, Golub and Leeson for saddle point theory, Elman, Sylvester and Watton for block preconditioning in fluid dynamics, and the ILUT papers for the multilevel construction. Thanks for watching.